I welcome you all in this lecture on validation and verification of simulation models, which is a sub module for the course on modeling and simulation of dynamic systems. Okay, see, one question is always asked from the simulation experts, that whatever simulation results you are getting, whether it is correct or not, or how do you ensure that the simulation results are correct. Okay. So, in order to do that, we need to just have a little background of what these validation and verification of simulation models we mean by. See, the best thing would always be that whatever results we are getting through simulation, if we have some experimental data or some other source, say if you have the analytical results, okay, and if you can compare, that is the best way of verifying your model, all right. But let us see how we can do that. So, as I told you, one of the most difficult problem facing the simulation analyst is that determining whether the simulation model is accurate representation of the actual system being studied. And as I said, this is the question which is often asked to the modeling expert, okay, whether your model is a valid model or not. And if, of course, if your simulation model is not valid, then naturally whatever results you are interpreting, okay, those results are not going to be correct. So, your interpretation will be wrong. And so, validation and verification are the two most important steps in any type of simulation activity which one carries out. Now, if we look at the definition of validation and verification, see, validation is the process of determining whether the conceptual model is accurate representation of the actual system being analyzed. And here, that is whatever system you are analyzing, okay, or say whatever your physical system is there, and from that physical system you have replaced that physical system with an engineering system. So, whether your replacement is proper or not, okay, or whether the engineering system which you have made, okay, or the model which you have prepared, whether it is correctly representing the physical system or not, that is what is the validation, is the process of determining whether the conceptual model is an accurate representation of the actual system being analyzed. Okay. If you remember, during beginning of our classes, I gave you an example of a water tank being represented by okay. So, we have a water tank supported on the pillars, and if you could recall, we represented this system as a equivalent spring mass damper system. So, the validation basically means that whether this is the true representation, this is the true representation of this physical system or not. And verification is the process of determining whether a simulated computer programming works as intended. Okay. So, what results you are expecting out of it, okay, or whether your codes or computer programs are working as intended, that is what is known as the verification, or what we also call it as the debugging of the computer program. So, this is how it is. So, you have the real world system, and this real world system we prepare a conceptual model as I am telling you here, okay, and this process is what we call it as validation, okay, and this validation could also be called that if whatever real world system you are having, okay, and if your simulation program is truly representing whether that system or not, or the behavior is truly representing the behavior as expected from the real world system or not. So, this is what is called as the validation, and verification means that whatever conceptual model you have prepared when you are coding and you are getting the results, so whether you are getting it correct or not. So, this is what is called the verification. Now, techniques for verification of simulation model. So, let us see first the techniques to verify the simulation model. The use good programming practice, okay, when you are programming for something, there are certain good programming practice which one need to always follow, okay. So, when you are programming, use as many comment statements as you feel appropriate, so that the user can understand how the programming has been done, okay. So, write and debug computer program into sub programs. Instead of making or writing a very huge program, say of 1000 lines, it is always advisable to prepare the program of small size, okay, and that is what is done by what we call it as sub programs, or in some of the languages it is called function. You create some small functions, okay, or sub programs, and then you use those sub program or small functions. In general, it is always better to start with a moderately detailed program and later add extra details if required, okay. So, instead of making your program very much detailed at the beginning itself, okay, it is always advisable to start with a moderately detailed program, because if at the beginning itself if you will make a very huge program, and during execution of that program, if you certain problem comes or certain errors comes, then the debugging will be very difficult, okay, and you will be spending lot of time in doing that. So, this is the general suggestion. These are the good programming practices, that you provide good number of comment statements, write and program using small modules, okay, and start with a moderately detailed program, and when you are confident about your program, then of course you can go on adding the extra details. Use structured walkthrough. Get ready the program by more than one. Get read the program by more than one person. Okay, so you can ask some other expert also to go through your program. This is what do you mean by structured walkthrough. Okay, the advantage of this is that other expert can suggest you the alternate means of programming, okay, or alternate interpretation of your coded program. So, it is always helpful, and of course, his suggestions, his or her suggestions are always going to be helpful for the debugging also. Then use a trace. Okay, actually the trace is what do you mean by trace is that we try to get some intermediate results, okay, intermediate results from the program which you have written, and those intermediate results actually helps you in verifying your codes, because many times if you say that you are not getting the end result correctly, but if you are getting some intermediate results correctly, then you can at least identify the zone in which the programming error might be there. Okay. So, this is the use of the trace. Analysts may use a trace to print out some intermediate results and compare these intermediate results with hand calculation or through some other means to see if the program is operating as intended. Check simulation output for reasonableness. This is what mostly simulation people do. Okay. That is, one should have the idea, one should have the intuition of what type of results one is going to get for the given conditions. Okay. So, for example, if I take the case of say simple spring mass damper system as I have shown here, okay, we should have an idea that say simple spring mass damper system, the system equation we know is mx double dot plus bx dot plus kx is equal to 0. Say if I am talking about the free vibration case, alright. Now, here we know that b square minus 4 mk as we have seen earlier, the characteristic equation corresponding to this system will be ms square plus bs plus k is equal to 0, and the values of s will be plus minus minus b plus minus under root b square minus 4 mk upon 2 m. Now, what I am telling you that we know the behavior of this equation will depend on this value b square minus 4 mk. Alright. So, whether it is going to be if b square minus 4 mk is greater than 0, then you are going to have the overdamped case, okay, and if b square minus 4 mk is equal to 0, then it is your critical damped case, okay, and if b square is minus 4 mk is less than 0, okay, then this is going to be the underdamped case. So, what I am telling you that we should have the intuition that okay, if the parameter which I am using for b, m and k, and these parameter values are such that they are going to make this type of condition, they are going to create this type of condition, then it is going to be an overdamped case. Okay. So, from these values we should have the intuition or we should know that what type of result we are going to get, okay, and that helps a simulation expert a lot. So, this is what I mean by that, check simulation output for reasonableness, whether the result simulation result which you are getting it is reasonable or not. Run the simulation model for a variety of input scenarios. You can run it for different input conditions and check to see if the output is reasonable or not. Okay. And in some instances certain measure of performance can be computed exactly and used for the comparison, and these what could be these measure of performances, those we have already seen in our lectures, earlier lectures, that is the performance measure for the first order system and performance measures for the second order system. So, these performance measures can be computed exactly and they can be used for the comparison. Another very beautiful thing which one can do to verify the result is the animation. These animations are usually carried out using your simulated data. So, whatever simulation data you are seeing, okay, those simulation data or those data you can take, export, and you can use it in the animation software, okay, and you can see the actual behavior. visually by creating the videos or by seeing the different frames, animation frames, you can judge how your system is behaving. Okay. And let me tell you that this animation helps us many times, that that is whatever insight is not given by the simulation result, because many times it is difficult to interpret your simulation result. I can give you an example of say animation for the robot motion. Okay. Then how links are moving, how joints are moving, okay, where your end effector is going. Alright, all those things if you want to simulate, then simulation may not be giving the very nice representation of what actually is happening. Rather, if you do the animation of it, then you will be observing that what actually is happening with your system. So, using animation, the users see the dynamic display of the simulated system, and since the users are familiar with the real system, they can detect the programming and the conceptual errors, what programming errors are there, what conceptual errors are there. So, all those programming and conceptual errors can be checked and verified, and as example I gave you the animation for the robots. Okay. So, how the different links are moving, where the end effector is going, okay, all those things one can see animation through animation, and it is a very good visual representation, and it gives some sort of scenario or environment as if your real system is working. So, it really helps many times in checking your model. Then compare final simulation output with analytical results, if, of course, if those results are available. May verify the simulation response by running a simplified version of simulation program with a known analytical results. Of course, if those analytical results are available to you, it helps many times in verifying our simulation results. And if the results of simulation do not deviate significantly from the known mean responses, then the true distribution can be used. Now, after seeing the techniques for verification, now let us look at the techniques for validation of the simulation model. Now, if you want to validate the simulation model, one can adopt a 3-step approach for developing a valid and creditable model. These approaches are that is, the first is develop a model with high phase validity. Okay. The objective of this step is to develop a model that seems reasonable to the people who are familiar with the system under the study. Okay. So, what does this mean is that whatever model you have developed, that model should be reasonable, convincing. Okay. And this step can be achieved through discussion with system experts, observing the system, or the use of intuition. As I was telling you, intuition plays a very big role in your modeling and simulation activity. Okay. So, this can be discussed with the system experts and observing the system or the use of intuition. It is important for the modeler to perform a structured walkthrough of the conceptual model before Q people to ensure the correctness of the model assumptions. As I said, the models are always replicating the real world, but real world has got so many features that you cannot replicate everything in your model. Okay. So, the feature which is going to play a significant role in the analysis which we are doing, okay, we consider only those features in our model. Okay. And we can carry out a structured walkthrough basically that is to present the model in front of other experts to see the important assumptions or know about the correctness of the model. The second step is the test the assumption of the model empirically. Okay. The assumption made in the initial stages of the model development are tested quantitatively, and for example, if some theoretical distribution has been fitted to some observed data, graphical method and goodness of the fit test are used to check for the adequacy of the fit. Of course, this is what is done in the data analysis. Then we can carry out the sensitivity analysis to see that what are the inputs which are going to affect your output significantly, and then we should take care of those input. So, sensitivity analysis can be used to determine if the output of the model significantly changes when an input distribution or when the value of the input variable is changed. Okay. And if the output is sensitive to some aspect of the model, that aspect should be taken care more carefully. And the third is step is that determine how representative the simulation output data are. Okay. The most definitive test of the model validity is determining how closely the simulation output resembles the output from the real system. Okay. So, this is the most representative of the simulation output data. Okay. One can go through the Turing test can be used to compare the simulation output with the output from the real system. Then output data from the simulation can be presented to experts who knows about the system in the same exact form as of the actual system data, and of course, the experts can differentiate between the simulation and the system output. Their explanation of how they did should improve the model in your further iterations. Okay. And there are statistical method available for comparing the output from the simulation model as well as those from the real world systems. So, statistical method for comparing real world observation with the simulation data. These are the two basic approaches which are followed. One is the inspection approach and another one is the confidence interval approach. Okay. So, in inspection approach basically we run the simulation model with the historical system input data instead of sampling from the input probability distribution, and we compare the system and the model output data. So, both the output data are compared by comparing with the or by giving the historical system input data. Okay. The system and the model experience exactly the same observation from the input random variables, and this approach results in model and system output being positively correlated. So, what is basically done here is that you have the historical system input data for the both the cases. You feed this historical input data to the actual system as well as to the simulation model, and the system output data can be observed, and similarly you can have the model output data, and then one can compare the system output data and the model output data. Then there is another approach what is called as the confidence interval approach. This is a more reliable approach for comparing the simulation model with the real world system, and of course, this requires a large amount of data. Okay. Suppose we collect m independent set of data from the system and n independent set of data from the model. Okay. M and n can be equal. Now, let xj be the average of observation in the jth set of the subsystem data with certain mean, say mu x, and let yj be the output from the jth replication of the simulation model, say with mean mu y. Okay. So, the objective is to build a confidence interval, that is the difference between the mu x and mu y. So, this is what is done in the confidence interval approach. Okay. So, basically we try to find out the difference between this means of the system data and that of the output data, and this is what is called as the confidence interval approach. In fact, this may be only feasible approach because of the severe limitation of the amount of data available on the operation of some real world system, and here one must take care in interpreting the result of this approach. Okay. So, this is a very short presentation on how we are going to or what care we must take in validating and verifying our simulation data. Thank you.